Okay, good afternoon, everyone. We added some more power and oomph to that microphone, and we'll try yet another thing tomorrow, see if it works better. Can you hear me better? Yeah. Okay. Now the speakers, you need to speak into the microphone. It's better. Okay, so our first talk this afternoon is going to be from Chuck Mueller. He's going to talk about the database of earthquakes recorded in the CNA, Central Eastern North America, because a lot of those come from Canada. I have some handouts that they printed out. There's 40 of them, and I think we're about 45 people. So if you can share, that's fine. If you want a copy for yourself afterwards, ask Chuck, and we're going to make sure we can give you copies. But if you just want to follow along, we're just going to pass those along, and you can take notes and all that. So Chuck, the floor is yours. Thank you.
So advance with the buttons here?
Yes.
Yeah, the handout is the summary page from an email that Chris Kramer sent on October 20th. And so there's the summary paragraph and then a table showing what's available in the database as it's currently constituted. Unfortunately, Chris couldn't be here. He sent me some slides, and I added a few of my own, so hopefully I'll be able to give you a picture of what the current status is. I'll be followed by John Adams, Bob Herman, Gabe Toro, and Trevor Allen, who are going to talk about various other aspects of the data, and Bob Dara also is going to be talking at the end of the session. If you need another copy of that handout, we can work something out. I also have about 10 copies of Chris's full email, which is about a 7-pager. So if anybody wants a little more detail, we can do that. So just a quick overview: goals, data sources and processing, the progress on the flat file, some comparisons of a few magnitude 5s with some of the existing ground motion prediction equations, a little bit about Bouge, a little bit about site characterization, and then we'll close with some issues. So the goal is pretty clear to everybody, I'm sure. We're trying to make a database of ground motions for development of new ground motion prediction equations. The initial focus was on Central and Eastern North America, and we wanted to be complete at the magnitude 4 level, and that was sort of the initial focus that Chris had. And during the process, he's also collected some data and added some well-recorded smaller events. We're trying to also get analog data for other stable continental regions, and Gabe will talk a little bit more about that. An important goal was uniform processing, to include as much site information as we could find, some sort of consistent quality assurance process, and we were also trying to follow the NGA West approach as much as possible. As far as data sources, Chris's initial focus, like I said, was on this magnitude greater than or equal to 4 data from Central and Eastern North America since about 2000, when the broadband networks started to come into their own. And the initial focus was on the broadband data, of course, but there was also some strong motion data and some short period data that's of variable quality and usefulness for some of these earthquakes. This started about 2.5 years ago, and during the process, we've also had the 2008 Mount Carmel main shock and 3 aftershocks, which have provided some data. 2010 Oklahoma, 3 magnitude 4s, 1 magnitude 4 in Arkansas, and then, of course, the Val-des-Bois earthquake in June. And Chris also, at that point, began to look back and find some data from important earthquakes, starting with Saguenay and through the 1990s, Mount Laurier, Cap Rouge, and Côte Nord. And the data for those came from the Lamont Strong Motion Database and Geological Survey of Canada. That's strong motion data primarily. The current focus is on smaller earthquakes, 2.5 to 4 Central and Eastern North America since about 2000, with the provisos there are at least 5 recordings within 100 kilometers. There's also some recently released Canadian strong motion data, Riviere de Loup, and some Nahanni data that he's added. And then he's gone back and, with the help of Gail Atkinson and others, gotten some data from some of these older earthquakes, 1925 Charlevoix, 1929 Grand Banks, 1935 Temiskaming, and 1944 Cornwall, Messina. Big, important earthquakes, but with data of variable to poor quality. The modern waveform sources, he relied initially on the IRIS-DMC, where the ANSS, Lamont Cooperative Seismic Network, and EarthScope data reside. Also the Canadian National Data Center, and then other more local data sources like the Geological Survey of Canada for some of the important strong motion data, Memphis, St. Louis, Virginia Tech, the Weston data, USGS Netquakes, and some Hydro-Quebec strong motion data. For the older data, as I said, the Lamont Strong Motion Database, which is now defunct, but before it died, Chris managed to get the Saguenay data, or some of the Saguenay data, and some of the 1990 Mont Laurier data, and then also Gail Atkinson pitching in on these 4 large older earthquakes. And again, these data are such poor quality that it's only going to be longer periods that they're appropriate for. So to date, Chris has collected and processed data from about 70 earthquakes, and this is probably the key slide. This shows the current state of the flat file, and I don't know if I need to read these in detail, but the point here is that these are, for the most part, the recent data with the best quality and the most stations and the largest earthquakes that have been processed through to the flat file stage. And there's this code. If you look at the handout, there's this ICQCF code that's listed above the table. I is initial data collection and processing. C is passband corner selection. Q is quality assurance test completed. D is GM wrote D program run. And F is event QA plots, QA'd and plots finalized. And that also stands, I think, for flat file, because if you look at that table, the only events that are in the current flat file as of October 20th are these ICQDF events. We can come back to this if anybody has any particular questions, but you can see these are sort of the most important earthquakes. So about 3,600 records from these 20 or so earthquakes. Gabe will talk about this more later, so I won't dwell on this. These are the sources of possible data from other stable continental regions. Trevor Allen has been collecting data from Australia, and he'll talk individually about that. Chris has some data from the Bouge earthquake. Julian Baumers helped us with Europe and South Africa. Vladimir with Russia, and Bob Herman is our contact for Korea. And I guess we need to know if there are other areas we need to be considering. This is the basic magnitude distance plot, and I honestly don't know whether these are, I think this is the complete data set, not necessarily things that are currently in the flat file. But you get some idea of where we're at in terms of distribution and the usual limitations of close distances at all magnitudes in this case. And it occurs to me in looking at this plot that maybe the less than magnitude 4 earthquakes aren't really bringing a lot to the story, but we can talk about that also in terms of priorities for where we want to put our efforts in the future. Will it be collecting more magnitude 3 type data? There are a few blue points here. Up at the top is the Bouge data, and those are engineering seismoscope records. And then under the P in components is another blue circle, and that's Gosley. This is just a map of, Chris calls them selected earthquakes. This is 66 events. The red stars are magnitude 4 and greater. The blue stars are smaller than magnitude 4. And this is the recording stations so far, a broad distribution. You can see the transportable array from EarthScope in the western part of the slide that's contributed some data for some of these Oklahoma and Arkansas events. Well, one thing I should have mentioned back here was if you look at that 2010 Lincoln, Oklahoma magnitude 4.1 event, 310 stations reporting, that's been the main contribution is the EarthScope array for that event. far as processing, Chris has been using SSHAC. The procedure goes something like download the uncorrected waveforms and pull 0 files, plot the waveforms and review them for obvious problems, do an instrument correction and an initial filter with 0.05 and 100 hertz corners, and then look at signal and in particular pre-event noise spectra, and I'll show an example of this in the next slide, and select final filter corners based on this signal-to-noise analysis. And then some final bandpass filtering based on those corner selections, and then extract the NGA ground motion values that go into the flat file, namely PGA, PGB, PGD, and 105 spectral ordinates. The instrument correction and filtering, he removes the mean. He does a linear detrend in the 2% cosine taper, uses the SSHAC transfer command and the pull 0 files to remove the instrument response. As far as filtering, there's a frequency domain acausal cosine tapered bandpass filter within the SSHAC transfer capability, and he's checked these results in comparison with some of Dave Boer's processing and filtering, and he gets the same results. So here's an example. It's a little hard to see, but there are actually 3 traces there. There's a green one is a particular kind of filtering that he's done. Blue is the SSHAC Butterworth that Chris uses, I think, and red is Boer's Butterworth 4-pole filter. And the traces essentially overlap. You can see some differences right before the initial sharp onset there, but otherwise Chris is comfortable with claiming that the results are similar for these approaches. This is the quality assurance that's been going on within Chris's group. Again, he examines the original waveforms, looking for clipping, distortion, other obvious problems, missing data, spikes, and so on. Looks at signal to noise and gets a final filter selection. Reviews the acceleration and displacement record quality and adjusts the filtering as needed, and plots PGA, PGB versus distance, and looking for problems, outliers, and so on. And then he builds a waveform quality table for each event. This is an example of that signal-to-noise analysis. You can see a section of pre-event noise is plotted in blue, and the signal is plotted in red, and the places where the spectra coincide in frequency are used to guide the choices of the filtering frequencies that are used. And this is done on a record-by-record basis. So some comparisons with the existing ground motion relations. These are magnitude 5 hard rock attenuation relations from the suite that was used in the 2008 update of the central and eastern U.S. part of the national hazard maps. This is for a dip slip fault. And he's plotted data from 3 earthquakes here. These are mixed sites for 2002 Au Forks, 2005 Rivière-du-Loup, which is actually I think about a 4.6 magnitude earthquake, and then the 2010 Val-des-Bois. Au Forks is dark blue, Rivière-du-Loup is red, and Val-des-Bois is that sort of turquoise color. Here's the 2008 Mount Carmel event. In this case, the relations are for a moment magnitude 5.2, knee herp for BC, boundary site condition, vertical strike slip. And then for 1 second, spectral acceleration, again, the same 3 magnitude 5-ish earthquakes, mixed site conditions, and the relations from the 2008 CEUS national maps for dip slip. And again, Rivière-du-Loup, which lies kind of below the curves in most cases, is a magnitude 4.6 earthquake, I believe. And here's Mount Carmel, the 1 second comparison. A little bit about Bouge. He cited 2 papers here, one by Bowden and Horton, 2004, and another by Bowden and others, 2004, about the aftershocks. The point to be made here, I think, is that for the main shock, they're finding stress drops in the 150 to 200 bar range. based on various approaches. For the aftershocks, the Bruin model seems to fit fairly well. Stress drops are 150 to 200 bars or so. And the ground motions are, according to their analysis, the propagation part of the problem is similar to Central and Eastern North America in terms of the geometrical spreading and the Q. And these are some comparisons of the national map ground motion relations for a moment magnitude 7.7 against some of this data. And this is engineering seismoscope data. And in this case, everything's been adjusted to a firm rock site condition. Sorry. This was for PGA. And this is for 1 second. So again, he's collected waveforms from Central and Eastern North America, magnitude greater than or equal to 4 since about 2000, mostly broadband data, supplemented with some other kinds of data. Also strong motion data and others from some older events. The current focus is on the smaller earthquake data. Again, the broadband focus with 5 or more stations within 100 kilometers, plus some of this older data I talked about. The trends for magnitude 5, short periods match the current ground motion prediction equations fairly well. Long periods plot a little bit below. And he finds similar trends for Bouge. Just a bit about site conditions. I think Chris collected everything that was available to him in terms of VS30 measurements at the sites that are included in the database, but only about 20% of those sites have VS30 data or other kinds of VS measurements. I think he's given all that information to the geotechnical working group, and it's going to be up to them to carry this part of the problem forward. Maybe a little hard to see, but this is just an example of some of the sites in the Mississippi embayment region and a little bit broader region. The red sites are stations, and the blue ones are those that have VS data. And so it's some, fraction of the data, and he claims similar patterns for southeastern Canada and South Carolina. Again, about 20% total. So issues. Are we exhaustive? Are we representative? Should we be focusing on getting data from additional small earthquakes, additional older earthquakes? What about some of these large events near SCR boundaries? And I guess some people would put Bouge into that category. What about data sets for special studies, the kind of things that Bob Herman's going to be talking about? Chris claims not enough time or money to be exhaustive. That's my question mark. I asked him specifically whether we're exhaustive for that magnitude 4 and greater since about 2000 criterion, and he says yes, we are in that case. But we can be representative of available source regions. Do we need more small earthquake data? Data are available in New Madrid, Oklahoma, Mount Carmel. Should this be a focus? He's currently adding some of these events down at the bottom, September, New Hampshire, another event in Oklahoma, other events in Arkansas. We talked about adding some data from Walt Silva's catalog. This is 1976 to 1991, and I'll show a table in the next slide. Should we be including events from this data set with only 1 or 2 stations? Use distance less than 15 kilometer records down to magnitude 2.5 or some other cutoff. And a lot of these data are vertical component only, and how do we judge the value of those? This is the table, and you can see in that right-hand column a lot of them are vertical only, something we need to discuss in terms of setting priorities. Large events near the SCR boundaries. Gosley is currently included in the data set. Talking to Vladimir, this 1991 event in Georgia is probably not appropriate for SCR. Are there others that we should be considering? And then QA issues, which is something we haven't really gotten to within the group, but now that we've got a flat file to work with, we need to start talking seriously about this. Chris has done his part in terms of getting things into the flat file, but I think it's probably the role of folks like me and Gabe and others to consider what we need to do to extend the QA process beyond Chris's group. And I'd like to have a little conversation, I guess, about how NGA West did it and what we might do to copy their approach. And that is it. Thank you.
Okay. Thank you for the clear review and also for listing all those discussion points. We're going to keep the discussion for after the end of this session, and we're going to lump all that together. We might bring back those slides with questions there. Next speaker is John Adams from the, it's funny, it's my country, and I always want to mess up the Geological Survey of Canada. That's how you say it, right? Because I know it in French. They even gave me a prize when I was a
Commission
student.
Géologique
Canada, exactly.
Limit of my French.
Thank you.
Thank you. I've heard that this talk is a little bit AGU-ish, so I'll take you through it, but hopefully it won't bore you. And I think it's important to think of the context of the new data that's arrived. So I'm going to talk a little bit about the context of the earthquake, the records that have been released. Okay, the records that have been released, their early impact on eastern ground motion prediction records, and the unreleased records. And what I would say is that considerable work has to go into accessing the records and documenting their context before they should be used. In other words, don't just throw them into a statistical pipeline. And I really like what Chris has been doing in terms of the processing of the records and looking at each one. So this earthquake was magnitude 5. It was about 55 kilometers away from Ottawa. The largest aftershock is only 3.3, and we don't think there's going to be much useful information from the aftershock. The bad news is it was the strongest shaking in Ottawa's history, right? 150 years. But the good news, it was much, much less than the current earthquake design. The felt area was way down into Kentucky, felt by about 59,000 people from the combined USGS and Canadian Did You Feel It? It seems to have been felt much further to the southwest and the northeast, and my guess is this is going to come out as a directivity factor. And I think directivity on magnitude 7 is a pretty important thing to be thinking about. In terms of the felt intensity, we know that the shaking on soil is considerably more. There's an earlier aftershock shown in the top corner there. But we have a lot of very good geocoding now for felt intensity data within the city of Ottawa, and we should be tying that back. There's a paper from Powell and Atkinson already submitted to BSSA on doing that. In terms of the earthquake history, it's the strongest one we had in Ottawa. In terms of why it happened, we think that this earthquake happened under that blue line, which was a hotspot trade. North America went over a hotspot, the ground was raised up. And it's a fairly typical earthquake for this particular region. It lies in an area where the trends are more or less parallel to that direction. The earthquake focal mechanism in the top right from Bob Herman, I think, derived within about 3 hours, commendably fast. Yeah. So we do know that this was about 22 kilometers deep thrust mechanism. It's a very typical sort of earthquake, so that's good news. Earthquakes like this happen about every 50 to 70 years within 250 kilometers of Ottawa, but this was much rarer than that. The fact that it was only 50 kilometers away makes it much rarer. And if we do the seismic hazard assessment, this comes out to be about a 1 in 150-year shaking, which is, as it happens, is more or less consistent with the 150-year historical period. In terms of aftershocks, lots of aftershocks, I think 300 or 400. The decay with time has been fairly rapid. We've got a seismometer that we installed very rapidly, and together with some field gear, it's staying there. But the largest one was only 3.3, and in fact the closest digital instrument was not installed at that time. So the aftershock sequence for this is pretty uninteresting. So the field recorders, we've actually got continuous strong motion from the station at VDBQ there, which is about 6 kilometers away. 6 kilometers like this and 22 kilometers down. So it's a fairly good takeoff angle. And I would say that the data is relatively uninteresting to date. So this is what happened. Lots of people pouring outside because it was a strong earthquake. They didn't know what to do. Sign-out sheets from the local school, a great excuse for going home. Damage within Ottawa and surrounds, basically chimneys, things thrown off, so that was fine. I've just learned that there was a spill of toxic mercury at the museum. A lighthouse which uses mercury to float its mirror was moved from the Atlantic coast to Ottawa, and then about a kilogram of mercury spilled from that earthquake. And I've challenged some of the people back home to actually do the back analysis of the sloshing that causes mercury to slosh out. Interesting problem. Probably not very much in the way of structural damage. People were worried because of the chips and the cracks. However, closer to the epicenter, there was an embankment failure. This is an embankment across a reservoir that actually collapsed. And we've got a couple of large landslides. One of them here on the left-hand side is the landslide where the guy's house slid into the river, and then it backed up the stream and flooded a little bit of land. But the most dramatic landslide was about 400 meters long. It's a typical regressive sensitive clay slide. But what is absolutely amazing is it actually happened the day after the earthquake. So there was a real lag between the earthquake and this slide taking place, and yet it's undubitably connected. It's just that whatever the pore pressures were doing, it took about 24 hours for them to set into effect. Okay, let's move on to the strong motion data. My co-author on this is Lan Lin, who has come along to some of those meetings, and because of her, we actually got the data out within 47 hours, which we thought was pretty good. Here's where the data has come from. The cluster on the bottom left is Ottawa. The cluster on the right is Montreal. And that involved visiting some ETNA stations to recover the data. It wasn't all online. This is the seismograph from my house. I have a Class C accelerometer in my basement, and about 8% G was the peak value. I'm on fairly thick clay. Here's the records from the Class C instruments, a rock record and a soil record. And then there's the equivalent ones in Montreal, where clearly the noise level, with both in terms of the instrument and the city, is pretty severe. Sorry, I drift back because I'm trying to read it. So if you look at the records here, we had about 4% G on rock in Ottawa, up to 8% in terms of PGA on the soft soil site. And in Montreal, it was considerably less, at least from the records that we had immediately. The weak motion records came out within about a period of about 12 days, so I think people had already downloaded some of those. Gail's added that data to the Seismo toolbox and applied it in recent papers. And here's the paper that came out in Seismological Research Letters September, October. The interesting Val-des-Bois data is this stuff here. Which plots above the ground motion relation, both at 1 second, which was a bit of a surprise, and also at 0.1 second. This data, together with the Mount Carmel and Rivière de Loup earthquakes, is fed into a paper by Gail and Dave Bohr, which is available on Gail's website. And the modification, probably of greatest interest, is that the ABO6 relationship has been transposed into ABO6- by using a higher stress parameter. So this was an adjustment to make the relations fit the data better. Now, I just want to talk a little bit about the other data that's not released. The data which is online from the Geological Survey is relatively easily accessed and processed. But there's a lot of other data out there. It's an amazing number of people that are running seismographs of one sort or another. There's quite a lot of discussion back and forth talking to these people, actually getting the data and then finding the metadata to go with it. And so this is data which we have not yet released. We were trying to do another edition of the data file releasing. So a bedrock seismograph LSQ1, which is at the cottage of one of our seismologists, that's a pretty good record and didn't clip. And it's on hard rock. It's sort of about 2.8 kilometers a second nice. Really nice stuff. There's some potential records from Nanometrics in Canada because they have seismometer testing facilities, and we're running both seismometers and accelerographs at the same time. Distances up to about 70 kilometers. At Parliament Hill, these are the heritage buildings for the Parliament, and those towers you see there, the one on the right-hand side is a 95-meter high tower, heavy stone masonry, and they've been instrumented to find their response. They're instrumented both at the base and up the towers. The base is not really it's certainly not a free field record. It's not even always clear if it's actually on the ground itself, but they're quite interesting records. Here's one of them, the north-south component, about 4% G, which is very similar to the free-field Ottawa record, and it has very much the same sort of characteristics. If you look at the table at the bottom, you can see the amplification up the structure, and the tallest one got up to about 0.5 G, if you believe the record. I'm still a little bit dubious of that. I think it's worth being skeptical. And I think all of these happened without damage. In terms of response spectra, the amplification by the structure is really quite extreme, as you see from the peaks. The dominant period is about 0.6 seconds for this 80-meter tower, and that's quite consistent with the ambient noise. Okay, free field record in Montreal at Gas Metro. This record is a little bit strange, and for a while we thought it was actually contaminated by structural interaction. But as you can see, the site is well away from the main part of the plant. We think this is a rock site, but we can't be sure that there isn't like 2 meters of clay underneath it, and that might have an effect. There are the records. It was 1.5%, which is more than we actually got on the records that were quickly available. And what seems to me strange here is that the vertical component is so small relative to horizontal. The frequency content is very high in these particular records. However, they're actually perfectly consistent with the Napierville record of a magnitude 4.3, slightly closer distance. The amplitude is twice as large as the Val-des-Bois. But you can see the relative motions are very similar. But this is a very interesting record, and I don't think we fully understand it. A record from Hydro-Quebec, around 70 kilometers distance on soil, 4% G on soil, that's probably not too unreasonable. A record from a deep soil site, John Shore Road. This one here clearly clipped, and it clipped for about 100 seconds. And that really did surprise me. It's possible that there's a little bit of information there in the P before it clips that would actually be useful. And then some people at Carleton University and Geological Survey were doing ambient soil surveys at the time, and so they set out an instrument, and they happened to get this fantastic record at the bottom, just accidentally. So you look at this, and it has a 3-second period, and you shake your head and you wonder. And the answer is that it's come out of a clipped process record. Right? So you can't always take the records that people give you on face value, because the people who gave us the record said, you know, here's the record. And it was only when we went back to the raw records that we found that it was, in some fashion, this clip record had been processed into something that looked kind of real. So here's the summary slide. I'm still within time here. 1 in 150-year shaking. It's only 1/5 as strong as the current building codes. The spectra of this earthquake is down here relative to the actual design levels in Ottawa. So that's good news. And I would like to say I think it's an excellent data set, but it does raise questions about the amount of thought that goes into putting data into the database before you actually use it. Thank you.
Okay, thank you. The talk was good, but almost too interesting for the purpose of this workshop. What I'd like to bring back up as a question to discuss in the discussion, John, you mentioned that outside of the overall data that already has been compiled, there's other sources of data for the Val-des-Bois earthquake. And if we could discuss that in the discussion and bring that back up, that would be great, because that's something we could use. Okay, the next speaker is Bob Herman.
Thank you.
Thank you.
I'm going to start out by saying that when anything happens that's of interest, I usually send an email to Chris Kramer, and you're going to see some of the same data sets that he's already processed. So what's happened in 2010, been source inversion to get moment magnitudes and mechanisms, data on earth structure, which is important, and ground motions. Reason for doing source mechanisms or what it provides will be get a good moment magnitude, which is necessary, get a source depth, which I believe is much better constrained than anything from the network, and to learn something about the folding type. The red beach balls on your left are the earthquakes for which I had focal mechanisms this year. You can see that we had the one in Quebec, we had Illinois, New Madrid, Arkansas, Oklahoma, and some in the western U.S. The figure on the right indicates the direction of maximum compressive stress, which is not of interest to earthquake engineering, but a little bit more important. If you look at the colors, blue indicates the thrust mechanism, meaning earthquake on a dip-slip fault. The red indicate normal faulting, again a dip-slip fault, whereas the green are indicating mostly strike-slip mechanism. So there is a regionalization of the source type that is apparent in this part of the world, and that may have implications on what ground motion scaling is at short distances. Whenever there's an earthquake, I look at the surface waves generated. This is somewhat of interest to this group because one of the requirements is to define the response vector between a 10-second period and presumably some very high frequency. So the surface waves are providing some of the long period information on the response spectrum. They also provide information on crustal structure, and I'm just going to show you some of the dispersion measurements, some results that we've obtained. Got a comparison of Rayleigh wave and Love wave dispersion measurements, both from St. Louis U, which are the black dots, and from cross-correlation ground noise, which are the red dots, versus two models that I use for source inversion. I just want you to look at the dispersion curves for central Texas. I think it's somewhere a little bit northwest of Houston for that map coordinate, central Oklahoma, and something in the Kansas-Nebraska border. If you look at the shorter periods at the left of each figure, you'll see that there are big differences. That indicates that the upper crustal structure is quite variable just on this sort of a north-south line, longitude 96 west, going from the Texas Gulf Coast up into the Great Plains. Ground motion recordings. A lot of new instruments are out there. The transportable array is in the Midwest right now. The instruments are roughly at the western border of Missouri. You also have installations, some netquake instruments near Oklahoma City that have caught these magnitude 4 earthquakes and a number of the smaller earthquakes at short distance. There is a swarm going on right now in Arkansas that did produce a magnitude 4 event, but there's no real strong motion data in close or no strong motion instrumentation in close, and it might behoove the NRC to encourage the USGS to put some of these netquake instruments out in that area. I'm just going to give you an idea of what is available in the data sets. Chris Kramer is already using some of these. They're going to be in his tabular data, but perhaps for the modelers here, you can get some sense of what is available in different frequency bands as a function of distance. I have a little PDF file, about 40 pages. You're not going to see all those figures in this presentation. What I'm just going to do is show you what is in different frequency bands for a transverse component of ground motion for one earthquake. So this is a map showing all the broadband data that I have in hand for the magnitude 4.3 earthquake last month in Oklahoma. The big swath of red stations in the Midwest is the transportable array. This is amplitude versus distance. Transverse component, narrowband pass filtered at a 4-second period. So you can see there's a lot of data beyond the 100 kilometers, some data at shorter distances. Just for perspective, I'm plotting the predictions of the Frankel 96, the Atkinson Bohr 95, and the Atkinson 2004 models. If you go to 1 hertz, there are some differences. You know, the models do not really go out. They're not really applicable beyond 1,000 kilometers, but there seems to be a need for a little bit greater attenuation out to larger distances. At 3 hertz, There are differences between the Q value in the Atkinson model of 2004 versus what's in Atkinson 495. And if you go up to 8 hertz, you can see the need out at 2,000 kilometers for doing a data setting before making plots. Another thing that can be done with the data sets that are available now to be for Chris is to maybe look at effects, Gulf coastal plain versus the stable interior. Here I've taken the same data, the same plots for the Oklahoma earthquake and separated it according to azimuths, those that went up in a wedge between northeast and northwest from Oklahoma, and those stations in a wedge that went southeast to southwest. Those going south in the coastal plain are red, and at 8 hertz out of the larger distances, 600 kilometers, it looks like the motions are a bit smaller. Perhaps some of the group might say that's not a major difference. For all practical purposes, we don't have to worry about a Gulf coastal model. So 2010 has yielded significant new data that can test scaling with distance and scaling with, let's say, moment magnitude up to the maximum in the data set, which is a 5.0 for the Quebec earthquake. Looks like we have data sets now that can test the regionalization. Some of the lessons, if there are swarms, it'd really be good for somebody to put out instruments with the likelihood that you might capture something of interesting. And then what might we expect in the next few years as a transportable ray moves across the Midwest? Perhaps in the next year or so, there might be another magnitude 4 right in the central U.S. that would be well recorded by the transportable ray. So, thank you.
Okay, sorry about that. Thank you. Now we'll have Gabe who's going to focus on data that's available from other SDRs.
Thank you, Kristen. I hope my voice will last my presentation. I'm kind of losing it. So the situation here is that we have very limited data in the central and eastern U.S., so it makes sense to look at data in other similar or analog regions. It's an obvious thing. But as usual, that concept creates problems because the concept of analogous region is tricky, and there's never something that is identical to the region of interest. And so as you expand the region you're going to look into, you get more data, but at the same time you may be mixing data with different characteristics. So you always have to be careful of that balance. And in addition, in the concept of ground motions, I think the idea of analog should be considered in terms of the different dimensions it has. You know, it's almost that each subgroup within this study needs to look at the issue of analogs perhaps in different ways. So, for example, some region may be analog to the central and eastern U.S. in terms of source mechanism and depth, or in terms of scaling, and so on, Q and other characteristics. So I think the definition of analog, in some cases, especially when you get to the boundaries, may be very much theme-specific, something we should keep in mind. Something we're using at least as a starting point for the definition of analog regions is the concept of stable continental regions, which was initiated or proposed by Art Johnston for EPRI in the early 90s. And they defined it in terms of regions that in recent geologic times have not experienced significant deformation or other forms of action. So I think that have been stable in recent times. The long definition full of geological terms, which I don't quite understand. That is true. But I think it was a useful definition. It was initially proposed for maximum magnitude, but I think we can use it at least as a starting point in this work. Here's a map of the stable continental regions. This was developed by by Ross Wheeler. Gives you an idea of what the regions are. And here's a more recent one by Schultz and Mooney, and it shows you, by the way, that there are at least 3 different characterizations or subdivisions of the stable continental regions. You can think of the truly non-extended crust. You can also think of the rifted continental margins near the edges of these SCRs, and there's also some interior rifts. In fact, you can go a lot further in that, and in the EPRI work, in Johnston's EPRI work, these regions are subdivided into 265 different domains. In recent times, Schultz and Mooney did not change the boundaries, but updated the catalog data. That's useful for the NMAX perspective and for other issues of understanding the relationship between seismicity and stable continental regions, not very useful for this project. And more importantly, the Central and Eastern U.S. seismic source characterization study, again, did not change the boundaries, did not change the subdomain definitions, but updated the characteristics of these zones. So it looked at recent information. Of course, these characteristics have not changed in 20 years, but the data of those characteristics have changed. So they reevaluated each one of these subdomains and assigned different values of the parameters like age, stress state, etc. And one important consideration then is these definitions, these boundaries, these geometries have not been updated since that time, and there may be some new information on those issues which, again, might affect events near the boundaries. In addition to that, the design project digitized these boundaries, and at some point those will become available when the project is complete. Now, let me get into, once we talk about the general framework, let me talk about specific data sets that we have collected or we're in the process of collecting, and mostly the latter. The poster boy case is the Australia case. We have excellent cooperation from Trevor and from others in Australia, and they have, again, Trevor will give you more details about the data later, but there has been a lot of data collection that has been gone on. In addition, Paul Somerville did or is doing an assessment of which portions of which events in Australia should be considered representative of the conditions in the Central and Eastern U.S. In other regions, we haven't gone that far. Well, actually, in Russia, we have some data. Vladimir Grazier has been very useful in providing context to some of the people there. We have data from Gasly, and they are already in the database. There are some issues with those data, though. For example, these are 1-second seismographs, which is not the ideal instrument. Just this morning, I learned from Paul Spudich that the Gasly event might have been a gas-induced event. So we have to think, well, is it a tectonic event? Is it representative of the conditions there? That's something that needs to be looked at if that record is going to be important in determinants as part of the models that are developed. And that's the kind of questions that come up and are more difficult to answer when you're looking at events halfway across the world. And all the papers written in a different language, etc. Most likely, this event and many others are near the boundaries of SCR. So the judgment needs to be made for some of these key events. Is it representative or not? In Europe, we're not that far. Again, this is the place where we're at the stage of making contact with people, talking to people, getting commitments from people, but we have not obtained any data, and we need to start moving in those areas very quickly. And the emphasis for this year and next will be collecting this data, and we need to accelerate the process. In the UK, we have been in contact with Roger Mawson, Brian Baptist, and his group, also with Julian Bowman, who have been very useful in this process. We need to involve other people, and we're in the process of working on that. One of the problems in the UK, and it may be a problem in many other locations, there's very little information on site conditions. We're also in cooperation with other efforts, international efforts from Jen, and Carola is involved in that process. And with Cher, we have been in touch with Fabrice Coton, and others. So we're keeping an eye. We're trying to avoid duplication of efforts in this data collection. As I'll mention later, that's not so easy, not as easy as it seems, as you'll see later. And here's a map of some of the data from the UK, or the data from the UK, based on a paper by Edwards and others. And it shows you that, for example, in the range of magnitude greater than 4, distances less than 1,000 kilometers, there are some data. Most of the data, though, are from smaller magnitudes, and from this map, you cannot see to what extent it has satisfied the other condition that we had of around 5 or more events within 100 kilometers. There probably are some, and we need to get our hands on these data. In Africa, we have been lobbying the South African, the Council for Geosciences, and all those efforts, again, from Julian and others, bore fruit last week. And they agreed to contribute data. They put some restrictions on those data we have to think carefully about, but they don't want the data to be disseminated outside of the project team, so we have to deal with that restriction. Their preliminary assessment, this is great, because again, they sent us a letter saying, yes, we're going to cooperate, which is nice, but in addition to that, they sent us, they already clear that they already did a lot of background work on this data. And so we know some events, the distribution of this data. There are some data that are useful for this project. Unfortunately, a lot of the data in South Africa, as we'll see later, are from mining events. And so those will be of no interest to us, at least as ground motion events. I guess you could learn something of the South African cross from that, but that's less useful. Other African data, we're still looking. Carola has been making contacts, and we're trying to use some of that. Again, it's not so easy sometimes, as we'll see later. From India, Chris Kramer has the data from Bush that I think that may be in the flat file already. I'm not entirely sure. Bob Herman has some contacts in South Korea. We need to move on that. It was mentioned earlier, I think from Joseph, that we have some contacts in China. Again, we need to start moving on all these contacts. And in addition to that, if anybody else has any suggestions of other data or other contacts from stable continental regions, this is the time to get those, so we can start making inquiries and talking to people and finding out what there is out there. So it's not too late right now, but it may be too late in 2 or 3 months. In terms of South Africa, just to give you an idea of the data, here is a map from this paper by Saunders and others, and it shows you that many of the events, well, there's no pointer here, I don't have a pointer, I don't know how to use it. Anyway, many of the events happen in the mining region, which is the area with the little squares, which are less interesting. More importantly, and these are data, actually, clearly. It shows you, and this is again data we just received from the South Africans, so clearly they have been working on these issues even before they told us we're participating. They were doing their homework. And it shows you the stations as triangles and some of the events by magnitude, the magnitude range. This other map shows you the same kind of data, but it's separated by depth. And that depth gives you an idea of which events are tectonic and which events are mine-induced. And as you see, many of the events are green or gray, which are, again, in the mining region, many of them mining-induced. And finally, this other set shows you the data, and again, the blue ones are mining-induced, most of them, and especially most of the ones within 100 kilometers are mining-induced, but there are some data less than 1,000 kilometers, magnitude greater than 4, which meet our requirements for data. And there are, in addition to that, it was on the previous slide, but I didn't mention it, there's some analog data that they haven't looked at, and they may or may not have the resources to look at, given the agenda or the resources and the time that this project has. But there are more data out there that could be available for this study. And the good thing is we are in contact with them. They agreed to cooperate, and we need similar cooperation from others. In fact, they have been extremely forthcoming. After they agreed to go, it's clear that they're very committed. In terms of schedule, as we mentioned earlier, again, the first year ending as of 2 months ago, it was Central and Eastern U.S., Canadian, and Australian data. A lot of that is done, and you'll hear more from Trevor later. In the second year, the emphasis will be again on other analog regions, other SCRs, and we have to complete the complete catalog of both regions should be done by September of 2011 when it will be needed by all of the various work groups in the study. In terms of issues and technical difficulties, first one that comes to mind is again, to what extent does these regions analog? In particular, boundary issues are important. These boundaries were drawn 15 years ago, so there may be more information that may redefine those boundaries that have not been incorporated so far. Issues of data quality and instrumentation become more critical when you're getting data from different agencies, different places, in different languages sometimes, different alphabets. And there will be limited information on site conditions. That's worse, again, in many ways than the situation we have with American data. There are also institutional difficulties. For example, as we saw with the South Africans, they may impose confidentiality restrictions, saying the project team can use the data, but the data cannot be disseminated. That creates a problem. It's not clear to me, and that becomes kind of in the lawyer part of the job, if those restrictions apply to the raw data or do they apply to the live data, like flat file. That needs to be determined. Because if it only applies to the raw data, then it's no big deal. But more likely they will interpret it as applying to everything. We also need to think of ways to develop mutual relationships with mutually beneficial relationships with the different investigators. And it's a matter of offering something in terms of meeting participation or in terms of other kind of mechanisms where there's benefit for them and benefit for us. Another factor, and talking to Carola last week was very interesting, there are other factors that limit cooperation. For example, you think, well, now that GEM and SHARE are in place, we can, in many ways, combine the efforts and avoid duplication of efforts and cover a lot more data. But then you run into issues like, well, because it's confidential, we have the data, but the donor agency does not allow us to distribute it. So if you want the data, you have to go back to the donor agency and get it from them. That's one issue. The other one, and we're all guilty of that, is the idea of, yes, we'll give you the data, but only when our project is finished, and we've done the QA on it, and so on, and so on. So that creates a scheduling issue. And also, as Chris Kramer indicated in Chuck's presentation, we may get to a point where we have more data than resources to process and digest those data. It's something we need to think about. It's a good problem to have, but it's still a problem. That's all I have. Thank you.
Thank you. So the next speaker is going to be Trevor Allen. And after that, we have one more speaker. And we're doing really good on time. So, and we're accumulating tons of discussion points. So hopefully we'll have a lot of interaction. Please, thank you.
Okay, thanks, Christine. All right. Well, this presentation is only a very incremental update from the presentation I gave at the Ground Motion Database Working Group meeting in September last year. So I apologize to the people who were at that meeting, but there are many new faces here, so hopefully some of the material is new to some. So I guess I'd just like to discuss some of the Australian data that I have already contributed to the NGA East effort, and also discuss some other data sources that could be potentially used by the effort as well. So the general outline of the presentation, I'll just go over a brief overview of Australian earthquake activity and its tectonic setting, which some of you may or may not be familiar with, the compilation of ground motion for data for prior studies, have a look at the station configuration within the continent, and also talk a little bit about some site class assessments which we did back in 2006 and also earlier this year. Then there's some newer data which hasn't yet been incorporated into the data set which has been contributed to the NGA East from the 2009 Korumburra earthquake sequence, and then potential other sources. Okay, so Just a general overview of the Australian continent and tectonic setting. Hopefully, okay, can everyone see that now? Roughly 2/3 of the continent from around about what we call the Tasman line to the west is Proterozoic and Archean rock, so it's very old continental crust. And we find that in some of this old Archean crust, we tend to have some of our largest earthquakes. So such as this zone, this is working here, the southwest seismic zone, historically we've had 3 surface rupturing earthquakes since the late 1960s to the 1970s, the largest being the 1968 Meckering earthquake, which was about a magnitude 6.8. Some of you may also be familiar with the Tennant Creek earthquakes, where there were 3 magnitude 6+ earthquakes in the one day up in the Northern Territory. And other regions of note, we have the Flinders Ranges seismic zone here, and along the Eastern Highlands, there's also a region of higher than average seismicity across the state. So some prior studies, my PhD was looking at earthquake hazard and ground motion issues in southeastern Australia. For this work, I compiled a data set of approximately 1,200 strong and weak motion records. So most of the data are actually from short period instruments. There are roughly 84 earthquakes between 1993 and 2004, which I analysed, and the magnitude range of those earthquakes were moment magnitude 2 to 4.7. And I'd actually just like to raise a fairly important point here, which I think hasn't been mentioned yet, is that these moment magnitudes were determined using my geometrical spreading and Q models. So the maximum peak ground acceleration for the data set was approximately 7% G for the 1996 magnitude 4.5 Thompson Reservoir earthquake. I did an analogue study in Western Australia as well. Most of the data from this study was collected from an earthquake swarm near the town of Burrakin in southwestern Australia, which is one of the areas that I pointed out before. There were 69 earthquakes between 2001 and 2005, and the magnitude range of these earthquakes was between 2 and 4.6 as well. Now, notably, I guess the peak ground acceleration for this earthquake was roughly 30% G on a horizontal component for a magnitude 4.6 earthquake. Now, that also brings into question the utility of these data as well, because they were all determined. The data set was pretty much all from an earthquake swarm. That means that the data collected is also very spatially clustered as well. So that raises issues with respect to particular site characteristics which might influence attenuation studies. So you can see here at the larger distances this becomes very apparent. So this is all one site, for example, collecting all of this data around about 100 kilometres. So the station, just quickly, the station configuration in southeastern Australia is probably where we have our densest seismic networks. It's a mixture of national seismic stations, which are the red upside-down tiers, which are operated by Geoscience Australia. And there are also quite a few proprietary networks operated by Environmental Systems and Services, which service the dam owner community. So most of these stations are across the eastern seaboard of the country. The Environmental Systems and Services network was established, or mostly established by 1993. The Australian National Seismic Network stations only started recording at about 200 samples a second since about 2006. So, and prior to this, the data was only recorded at 40 samples per second. I should also point out that the national stations also all have strong motion and broadband instruments. I mentioned earlier that we conducted shear wave surveys at a number of our recording stations across the country, mostly across southern Australia, so from Western Australia through to the eastern part of the country. The survey locations were conducted near existing seismic stations and also temporary networks. They were mostly undertaken at rock sites. And earlier this year, we extended these shear wave surveys to extend the data set in southeastern Australia. So the purpose of that study was to look at shear wave for different geomorphic regimes, also to examine high risk and urban environments, such as Newcastle, where we have the damaging 1989 earthquake, Sydney, and the Latrobe Valley, which is where we have a lot of infrastructure, power generation facilities in Victoria. We also did some surveys to examine increasing sediment thickness to see whether the VS30 values varied along particular profiles. All in all, we surveyed approximately 30 new sites this year, and about 10 of those were at seismic stations. This is just a map of the 2006 survey, so you can see that we did quite a few surveys in Western Australia, around the Flinders Ranges near Adelaide, and also across the eastern seaboard. So most of the newer recordings were on the east coast. I won't go through that in detail, but this is just an estimate of the VS30 and VS100 values from the 2006 surveys. Now, a data set that I haven't yet contributed to the NGA's effort is from the 2009 Korumburra earthquake sequence. So this is a sequence where we had two earthquakes of local magnitude 4.6, which occurred in March 2009. There are approximately 20 earthquakes from this sequence, greater than magnitude 2. 9 of those events were greater than magnitude 3. So the two major earthquakes in this sequence occurred on the 6th of March and the 18th of March. So following the first earthquake on the 6th of March, we installed the Australian Seismological Community installed 6 aftershock recording stations. So these successfully recorded the second magnitude 4.5 earthquake. So on one of the stations, the peak ground acceleration was recorded at 36% G for the vertical component and 24% G for the east-west horizontal component. And this is just a map here showing the distribution of stations from the earthquake. The epicenter of the earthquake was located here. This line out here just represents a distance of approximately 100 kilometres. So the earthquake was strongly felt in the urban region of Melbourne here, and these green dots again is the station distribution in the region. So this earthquake was quite well recorded. And sorry, these pins here are the temporary stations that were deployed following the first magnitude 4.5 earthquake. And this is just an example of the 36% G recording here on the vertical depth. The bottom traces the acceleration on the vertical component. Now, in a little bit of spare time, I did a bit of analysis looking at one station where we had a co-located short period and strong motion sensor. So the strong motion sensor was just a solid state acceleration recorder, and the seismometer was a Goulart 3 ESP. So I converted the velocity trace to an acceleration and did an overlay. In general, the peak accelerations are quite similar between the two components, but if you do zoom in, there are some differences. And I later found out after I had done this analysis that there are FIR filters which were applied to one of the instruments and not to the other. So that may account for the differences that I'm observing in the two traces there. Okay, so looking at potential data sources for additional earthquakes, since 1993, and again these are now in local magnitudes, there's roughly about 106 earthquakes between magnitude 3 and 3.4 that we could potentially go back and contribute to the data set. 31 between 3.5 and 4, 8 between 4 and 4.4, and roughly 7 earthquakes greater than 4.5 that could potentially be contributed to the effort. Additional Western Australian data. So there are digital acceleration records from the 1979 Caddo earthquake, which was a magnitude 6.1, which also have not yet been contributed. There's also data from another earthquake swarm in Western Australia in 2009, and additional, there are also aftershock data collected following the magnitude 5 earthquake, which occurred beneath the mining town of Kalgoorlie this year. For those who don't know Kalgoorlie well, it is actually quite adjacent to, I think it's the largest man-made hole in the world, the super pit. So whether this earthquake is potentially mining-induced, the jury is still out on that one. And in 2007, there was also another magnitude 4.7 earthquake near the town of Katanning, which actually left a surface rupture. And this image on the side is an interferogram of that particular earthquake. The final data set that could potentially be contributed is from a temporary seismic network that we had out in the Flinders Ranges of South Australia. There were 17 stations deployed over an area of about 100 by 200 kilometres. Approximately 160 earthquakes of magnitude 2 or greater than 2 were recorded, and 10 of those were greater than magnitude 3. The maximum earthquake, which occurred, I guess, in the northernmost extent of the network, was a magnitude 4.2. So that data is likely to be potentially quite useful for the effort as well. And we've actually recently completed a collaborative research agreement with the Australian National University to process and validate that data for use. But unfortunately, no assessment of the data has actually been undertaken yet. So that's essentially all. Thank you.
Thank you. And while I'm here, I'm going to go ahead and have one more rule. If you guys can think of leaving your cell phone away, because this gets all the, the interference, and it's already a pretty bad sound system. So that would help. The last speaker for this session is Bob Dara, who's going to talk about the collection of small magnitude data, mostly on the West, and how it's going to be used. Thank you.
Good afternoon. I'm going to talk about a slightly different topic. We're going to go from the East Coast to the West Coast, and we're looking at small magnitude data that we're going to collect in California. And this is work I'm doing at Pacific Engineering with Walt Silva. And our goal is to both collect and then uniformly process ground motion data from small to moderate crustal earthquakes in California. And this work, we're going to try and address a couple of significant issues for NGA East and NGA West. The first one we're going to look at is sigma and stress parameter analysis for comparisons directly with Central and Eastern North America. In the Western United States, we're very lucky to have a plethora of data at all magnitude levels from 3 up to the 7s. So we're hoping to use the abundance of data in Western North America to compare to East, and if we find that they're similar, we can use it as a guide in future analysis. And there's another project called NGA West, where the ground motion prediction equations have recently been looked at lower magnitudes, lower than about magnitude 5. And it's a task, too, to directly address the scaling from the ground motion equations to lower magnitude. And this also has applications to the hybrid method that Ken Campbell has proposed of moving Western GMPEs directly to Central and Eastern North America. We build on work of others by Brian, Bob, Norm, and Kofi Ado in 2010, and their work built directly on work by David Wald and Jack Boatwright. In their analysis, they looked at 188 earthquakes, moment magnitude 3 to 5.5, They looked out to 200 kilometers, and they were crustal earthquakes, so they only took top of rupture less than 20 kilometers. They were able to look at about 16,000 values from SHAC map, and they looked at basically 4 areas of the spectrum: peak ground acceleration, peak ground velocity, and then 3 hertz, 3.3 hertz, and 1 hertz. The purpose of our study is to extend this data, and here you see their data. The upper part shows the NGA data, which is up in here. The lower part is the data set added in the Cho et al. Study. So you see there's quite a bit of richness between magnitude 3 and magnitude 5, and well represented for distances between 10 and 200 kilometers. This just shows the geographic distribution. We're sitting up here, right here in Berkeley. So in Northern California, mainly Central California, a lot of faults along this Hayward-San Andreas system. Down here in the LA Basin, you have faulting along the San Andreas and the transverse system of faults in Southern California. Right. So what are we going to do? Our task is to supplement the data set with 6 aftershock sequences, 3 in Northern California. There'll be Parkfield, San Simeon, and Alum Rock. 3 in Southern California, an Alancha, an Anza, Yucaipa, and a Chino Hill sequence. We're also going to add more recent main shocks. Brian's study ended roughly in September of 2008, and there's been many more than this, but San Bernardino magnitude 4.5 earthquake, and another earthquake in Southern California near the Inglewood area, magnitude 4.7 in May of 2009. We're going to try to extend their data out to roughly 500 kilometers. They looked at basically 4 spectral values. We compute spectral acceleration in 112 periods, and Peer uses 105 of them, and then it'll also be available at roughly 11 dampings. Now we're going to collect 4 data sets from 4 different organizations, and I want to thank the people who cooperated with us in advance. We've tended to make non-traditional requests to the data centers. The first is the Berkeley Digital Seismic Network, and Peggy Helwig has been very helpful there. So in Brian's list, there are 59 main shocks from Northern California and 3 additional aftershock sequences. So we're looking at roughly 20,000 3-component accelegrams. We've only chosen the data from the BDSN with greater than 80 samples per second, and Peggy has reformatted the data for us into a SSHAC ASCII format that's easier for us to read. She's also done quite a bit of the event association for us, which traditionally we would have to request independently. So she was a great help. And the Berkeley Digital Seismic Network, if you're not familiar, includes data from Berkeley, USGS, and several other organizations in Northern California. Another big network in Southern California is Caltech, which also includes data from the USGS. From Caltech, we're going to get data from 134 main shocks, 3 aftershock sequences. Day 2, we're getting roughly, actually have already received about 20,000 3-component accelegrams. Again, sampled 80 samples per second. And their data, Ellen transferred to ASCII files for us rather than the normal SSHAC or other formats they would prefer to distribute the data to us in. Then we go to the more traditional data providers, and this is data set we're much more familiar with. However, we had to make additional requests for both from CSmith and USGS for data from smaller earthquakes than they normally wouldn't process. So we got quite a bit of cooperation from Hamid and Tony. Currently on the CSmith website, there's 58 earthquakes that will be in the process of downloading, roughly 2,500 3-component accelegrams. In addition, they're loading an FTP site for us with 53 additional smaller earthquakes as of 2 days ago, and that number is going to increase. And these are smaller earthquakes ranging from magnitude 3 up to somewhere in the magnitude 5s. These were data sets that traditionally would probably not be put on the CSmith website, and so they're giving us quite a bit of cooperation to extend the traditional strong motion data set in California down to smaller magnitudes. And this data is generally 100 samples per second data and in the standard CSmith or CSmith format. The final one is the National Strong Motion Program run by the USGS and Chris Stevens. And they're able to provide us with data from 84 earthquakes, about 500 three-component accelegrams, again in the standard format and high sample rate, 100 samples per second. So those are the 4 large data providers for data for us in California. And with that data, once we've collected it, we've collected all the Berkeley, all the Caltech data, and we will soon download the USGS and CSMIP data. So the next step is after we've collected it, which is basically done, we need to uniformly process the ground motion data from these earthquakes. And this is how we did it for Pier. It's on the Pier Strong Motion website. But basically, this is the flow chart for processing. And I don't want to talk in too much detail, but just go over, show you a couple examples of what the data looks like and what we do for it for quality assurance. This is from the Berkeley Digital Seismic Network, actually a station less than a kilometer from here in Byerly Seismic Vault. It shows great quality data from an Alum Rock main shock, which is magnitude 5.4. One thing that's different with the data from the networks is here we have 300 seconds worth of data, 5 minutes worth of data from the magnitude 5.4. Traditionally, from an earthquake of this size, we'd probably be looking at 60 seconds of data. So there's going to have to be some truncation of this data. If we process everything out to 300 seconds, it's going to produce a tremendous amount of data that will overload our system. This is another example. This is from a much smaller earthquake. This is from a recorder near Anderson Reservoir down near San Jose. It's a magnitude 4.1, the San Simeon aftershock. Here, you can see the earthquake is there, but this data, one of the checks would be looking at the time histories. This data will not be processed by us. But again, we have 360 seconds worth of data, extremely long data sets, much longer than we traditionally look at. Finally, one of the other quality assurance checks is looking at the Fourier amplitude spectra to determine where the noise is for for processing. We want to have as much signal as we can out to the highest frequency and actually out to the lower frequencies. And in general, in Fourier amplitude spectra, you see this nice two-slope coming down here on the vertical component, then it flattens out. Traditionally, we'd pick our first corner pick would be out here, trying to preserve as much long period information as we can. And then we look at the acceleration velocity, and particularly displacement time histories, to see if they're still dominated by noise. And if they are, then we'll move in the pick on the corner frequency until we get a record that looks good in displacement. We do that independently in all 3 components. We also do it at high frequencies. Here, near 80 hertz, there's a flattening in the Fourier amplitude spectra, and we would pick the corner roughly around 80 hertz for this record. And this is kind of our final products. This is from an earthquake magnitude 5 in Yountville. So we give acceleration, velocity, and displacement time histories. Here you see for magnitude 5 going out for 60 seconds. This is at the Treasure Island geotechnical array, a very soft soil site in the middle of San Francisco Bay. And one other thing we give is, this is a 5% damped acceleration spectra for the 3 components, again from the same earthquake. So just to summarize, this project is probably going to add about 200 main shocks between magnitude 3 and 5. In addition to the main shocks, we wanted to get about 20 aftershocks in each sequence. Over 6 sequences, we'll get about 120 aftershocks. We've collected somewhere near about 50,000 three-component accelegrams. Less than these will be processed due to either noise considerations or low amplitudes. We compute the response vector at 112 periods from 20 seconds out to 100 hertz and at multiple damping levels. Again, this just reminds you of why we're doing this project. We're going to look at sigma and the stress parameter analysis in Western North America, particularly California, to allow us to compare it with Central and Eastern North America. And we want to extend the we want to provide the data to extend the Western ground motion prediction equations to low RAM down to magnitude 3. and also some of the implications for the hybrid approach. And that's it. Thank you very much.
Okay, we're making good time again. I would like to thank all the speakers for this session, and I think they deserve an applause. So we're going to go to a 15-minute break, and after that we'll come back for discussion. We've compiled a list of issues that were brought up by the different speakers, and we'll go over those together. Oh yeah, and at the discussion time, please, we'll have all the speakers up front here, and whoever is going to interject and comment, come also up here, and we might end up having the whole crowd here, but it's okay.
Can improve it. Hey.
We'll give it a shot, huh?
Yeah, exactly. Anything that works.
At the point we can get feedback from the people on the phone, that would be great. Let it be in your way.
is a microphone test. This is a microphone test. This is the test of the microphone. This is a test of the microphone. I spoke pretty quietly. This is a test of the microphone. This is a test of the microphone. We're testing out the new microphone system. This is the new microphone system.
Un, dos, tres, testando, microphone, microphone test. 1, 2, 3, testing the microphone. This is a test of the microphone.
Now it's harder to hear. On the polycom. So we turn up the volume?
We'll go stand outside and see if you can.
Or maybe we can move the polycom to in front of one of the little speakers where you need it here.
I guess we can do that.
The problem is we speak so softly. Yeah, I mean.
Yeah, I just want to see if it's going to be a lot of work.
I think maybe that's a test.
I was thinking. Say something again.
This is a test. Testing 1, 2. Testing 1, 2. I don't have your phone. He has it, I think. Testing 1, 2. I think you might be. Testing 1, 2. We're testing the microphone. Sorry. We're testing the microphone. This is a test. Testing the microphone.
This is a test of the microphone. 1, 2, 3. Testing, testing.
But now you can't reach the microphone to hear.
But it's hearing it through the speaker.
Okay, you don't need to amplify the phone. Okay, you just
No, tomorrow we may have to amplify it. Yeah. You have the tape.
Somewhere. I'll find it.
And this just pushes it. Yeah, because you've got all the speakers on, yeah.
The conference has been unmuted.
Hi, this is the technical staff. We're trying to check in with everybody who's online right now to see how the audio is working for you and how the audio quality was in this session after lunch.
This is James Beela.
It went pretty well?
Well, it was better. I find that people who have English as a second language are harder to understand. The first, people need to, if they comment, they need to absolutely go to a microphone.
Okay, well, we switched the microphone for this afternoon, for this final session here. So hopefully that'll improve the quality one more time. If for some reason you think the audio quality winds up being worse, would you go ahead and just type in a chat later, which we'll check at the end of the session, and just to let us know if it was decidedly worse, because tomorrow we're going to reevaluate and try to choose the best system that we had that's achieving kind of optimal audio quality for both the people present as well as the people online.
I think you will find, though, you really need to get a clamp on cell phones and BlackBerries.
Yeah, we'll try to remind the speakers of that too. All right, does anybody else on the line have any other comments before we go? All right, well, thank you again for calling in online. We hope you enjoy the end of the conference today.
The conference has been muted.
Okay, everyone. Now's the time to regain your seats and get ready for discussion. Is the sound better? Yeah, really? Okay, good. Okay. Can I ask Norm to come over, and all the speakers from this afternoon to be able to interact and answer questions? Yeah. Norm has a slideshow. Did you put it on? Okay. So. Yep. Let's just wait for a second. Norm is taking the presentation we're prepared for discussion, and we'll suggest discussion.
What is the keep you away? What is the timing?
Like day 1 p.m. or something.
No, day 1 p.m. Norm, you want to start this?
Yeah, please.
Okay. Here's on the table.
Okay, so we didn't have questions for you while you were going, while you flew through all that material. So, is this the first one here? Okay. So these are some of the questions we tried to pull together for how we're going to use this. And let's start with some issues for Chuck, and that is, what are we doing for sites where we don't have a VS30? You said about 20% of the sites have VS30. What do we have for the other 80%?
Maybe a question for the geotech group tomorrow, perhaps? I don't know the answer. Yeah.
The answer could be you have a latitude and a longitude, and someone else has to figure. I mean, we haven't even called them rock or soil or anything along those lines. Is that correct? Well, okay, so we have shake map site conditions we could use. Okay, so the question is using shake map characterizations based on topography for the eastern U.S. Okay. Paul. We'll all be standing up here in just a little bit.
How about using the recordings at the site in a receiver function analysis to measure the VS30 using P to S conversions? We made it work, Bob.
Okay, I'm coming back. It's not the time for proponent discussions. That's a good point to bring up, and this should be addressed. No, I just heard comments like, oh, this doesn't work. Okay, so we're not going there. I know, and Paul is still my boss at QRS currently. Okay. So let's keep that on things we need to address. So we need to address VS30 at the stations for which we don't have it.
Some site class.
Some site class, some site characteristics.
I expect we're going to hear about that from the database group, right?
So the geotech group tomorrow, we can bring that issue again, but again, as part of this workshop, we have identified something that needs to be addressed. Paul is proposing an idea, and I guess that can be discussed further with the group.
Okay, the next sort of big issue was what is worth adding, right? So they've gone through a sort of current version of a flat file. Do we go back and add more of the older data, spend our time on that, or try to add other smaller magnitude data? It's kind of the trade-off that we have, or do we stop? Right, which would make Chris happy, I expect. The key, I think, thing for us to talk about is what is worth it. Right, so really to start to get useful things from us from the ground motion area, we need to have enough recordings per earthquake to be able to get a decent estimate of the site term out, or excuse me, the event term, so that we're not trying to say the whole event is a high stress drop based on one recording or not. And so we have used in the past, some ideas on our, say, NGA West, that if we have less than 5 stations, start to throw those events out as having unreliable event terms. And is this is that a meaningful cut? Does that throw out a lot of the data or make a useful partition?
I think for smaller than magnitude 4, that's the assumption that Chris is working on now. It's 5 or more within 100 kilometers.
Within 100 kilometers. Now, what about the older data? We talked about the older data. Is there, I don't know, Walt, if you're familiar with the stuff that they haven't included yet? Because there's an implication that there's still previous older earthquakes that you haven't gone back and included.
No, even digital. Again, data pre-2000, I think 2000 was the cutoff that Chris was using. There's some data, for example, that Walt has from the 70s and 80s, mostly 80s, well, actually 80s and 90s. And the April 93 data set, which I think Walt also included there, there's some data already processed and already used in some other studies. And the question is, how much do they add, and do we need them? My personal bias would be we should add them, again, probably within the same constraint. I think maybe it's useful to think of the thresholds we had set up earlier, which was all the magnitude 4 and greater data to 1,000 kilometers and 2.5 to 4 if there are 5 or more stations. And are those criteria still valid, or do we want to modify them for these older data, which are more difficult to process in some ways? Or do we want to stay with that? I think that's reasonable. That's a reasonable cutoff, personally. Any other thoughts about that?
Yeah, I guess John Adams, Geological Survey of Canada. Some of the earthquakes in the database may not be. It may be they should not be there. For example, 1929, I think, is quite problematic because, as far as we can tell, it didn't generate and propagate LG into the center of the U.S. And so its ground motions are effectively the amplitudes from SN phases.
So, but if that happens sometimes, why wouldn't we include that earthquake?
So that happens quite often for offshore events, but that just means you have to treat them separately, and the ground motion relation for the offshore events would not be the same as the relation for the onshore ones. And mostly, since we're building nuclear plants and other facilities for the on-land things, we're interested in the ones with LG.
Okay, so there would be some regionalization would be necessary if we were to include those kinds of events. Okay. Walt, is there, in your database that you have of these older events, is there a reason not to just bring those in, or is there a significant amount of effort needed still? And that hasn't happened then, is that? Okay. So Youssef is saying, and Walt is saying the data are from the older events. Many of them have been processed. There has been, though, no systematic checking to see which ones are included in the data in Chris's set and which ones are not. And we're going to have to do that this year then. Okay. Sure.
Let me ask Walt for a clarification. When you say redundant, you mean the same event being included, or no, or simply similar magnitudes and distances being included? Yeah, I think. Okay. So now we're saying we have too much data in the east, so we can afford to throw some away? That's news.
But, is there any reason if the data are processed as they are, why we would not include them? I mean, saying that they're redundant is fine, that we could say we have an area that is very well sampled, but why, I'm agreeing with Gabe, but if they're available, my tendency would be to include them. Okay, so the reasoning was older instrument, limited bandwidth, and maybe only vertical components. And that whole issue of verticals, I think we're going to need to talk about as to how much we want to rely on the vertical-only data set. Okay, can you put that down, Christine, as a task to evaluate essentially the relevance or importance of the additional older data that may be verticals only? I think if you have decent bandwidth and you've got horizontals, we ought to include them. Well, so coming back to the issue of offshore, according to what John was suggesting is if we're going to bring in offshore events, that's going to be a regionalization issue, that we may need separate ground motion models offshore. And right now, we don't do that, if I know correctly. Come up here if you have a question.
I have a question for Bob Herman. Approximately what percentage of small magnitude data that you have, 4 and below, is vertical only?
Perhaps
50%. 50%, about half of it.
And if we're talking about data, the importance of some of the events, Walt's database would be the larger earthquake with magnitudes greater than 6. Did you have any of those? Or did you just...
Yeah.
There is that table. Would that be useful?
Yeah, that would be useful for discussing his. In fairness, a lot of what was in Atkinson's early work is also vertical. So we can't get around from the history of the seismic networks.
We cannot hear anything.
Okay, I believe you. Well, I would think, looking at that they have been, for many of the regions, they have been supplanted by modern data sets of similar size earthquakes with more recordings. So my comment before is that if there was a larger event, I do not see in Eastern North America on that would be valid for not testing or validating a model, but for just a order of magnitude thing, such as the 1925 Temiskaming earthquake and other ones that are not in Walt Silva's catalog. So, the big problem is not what's happening at magnitude 4 and magnitude 5. The big problem is there's very little above a 6. So I guess the question is there anything in the older databases that somebody has collected that Chris could latch on to? There have been studies of the Temiskaming earthquake by Allison Bent. it might provide information at the longer periods, so on periods greater than 1 second, and it might be a value just for completeness or just to say that you have considered that earthquake. So, but looking at this, you've got there was a New York earthquake in, I guess, 2002, which provided more data than the Goodnote did. Nothing's happened up in New Brunswick since 1982, but there have been other well-recorded events up in Saguenay. So Saguenay's a problem of having a modern data set. The Olney, Illinois, you can say that that's been effectively supplanted by the Mount Carmel, Illinois earthquake 2 years ago. So you're not losing anything by not having that earthquake.
We may not, completely, but we may not lose something in terms of sort of attenuation, but stress drops is a big deal, trying to get the event terms out of all of it.
And sigma effect. If the recordings are believable, if the quality of the recordings is good enough to allow comparisons at some frequency range, it seems to me we should have them.
I'd agree.
All right, so the recommendations are bring this data in that are, we have enough recordings for, let's say, and use them as a minimum for checking the models that we come up with as opposed to deriving the models themselves. Okay? Then you have to come up.
George, have you received one series from Kramer, or he's going to send? I know you received response spectrum.
The flat file includes the response spectra. There was an email exchange at one point that discussed time series, and I know there is going to be a mechanism for doing that. I don't know the details.
Okay, one of the other needs that we have for this data, in addition to the median ground motion model, is for this sigma, and in particular, single station sigma. For that, what we're doing in California and other regions is you have to use small magnitude data to get enough recordings per site. We like to have 10, I think we can live with maybe a minimum of 5, but 10 recordings per site. And to get a reliable event term, we want at least 5, let's say, recordings per earthquake. So when we start to think about adding smaller magnitude data, so can I just go out of this back to where we were?
Are you a Mac person?
I am. This is very difficult. It's not intuitive, let me put it that way. So our small magnitude data here, I said, this is useful for single stations. We'd like, again, focusing on stations where we could get 10 recordings per site and earthquakes with at least 5 stations per event to get an event term out of that. So in looking forward, maybe we could go back and see stations where this looks like we would have a chance to do that and start to pull some of these together.
I have a question about the sigma. Do you put everything into a regression and then look at the residuals on the basis of the station? How does one determine the sigma you're talking about?
Yes.
Well, yes is not an answer to how, but I can accept it.
We do a regression, so we need a ground motion model. So we need let's say, at least a 2-step or a random effects regression, so we get an event term out. Mm-hmm. Then we'll have we're now using the term within event variability, but then we will calculate a site term. So each station, in a sense, we have a constant for every site.
Are you going to contemplate that this might be dependent upon distance and components?
The standard deviation?
Yeah.
Yes. In fact, there is indications you'll see on Thursday.
The small earthquake data, southeastern Canada and the central U.S. will permit you to do that for many, many sites.
Okay, so we have that. What our goal here is to compare the standard deviation to those that we're getting for California. It's been done for Taiwan, and for Japan, and Turkey, and where else? And Switzerland, and China, and Australia. We will do. We haven't been all that. So there's going to be a lot of areas we can compare. The key of all this is the single station sigmas appear to be much more stable or consistent around the world than when we're looking at the total standard deviation. So we have more hope of transferring data, let's say from California to the east in the single station sigma environment or approach. Okay? So if we gave a charge to the database group to look at the earthquakes and pick out those where we could try to get some stations with at least 10 recordings, and maybe those limit those to the additional data processing.
That's a new criteria.
Yeah, that's a new criteria.
All right. Then what John Adams was talking about, I will just call it the VDB, so I don't butcher the name.
Val-des-Bois. Oh, okay.
My French is not good. What additional data, John, do you have that's not included now? Because you indicated there was something there and it wasn't quite clear how much or...
Right. So part of the reason for making the PowerPoint a little long is that I did put figures in for some of those data sets. But we were sort of waiting to at least try and get the nanometrics data before we issued another version of the open file and, kind of tried to get it all out together. And we're negotiating with the owners to make sure that, in fact, they're willing to give us the data so we can give it on to other people. So that's really the hard thing. And then the other thing that's taking the time is learning about what site conditions are. Where is it placed? Is it really a ground record that you want to use? So in terms of timing, I would say 2 to 3 months from now, hoping everyone comes along.
Yeah. Then getting back to our same issue of single station sigma, you indicated a pretty large set of aftershocks, so a broad set of aftershocks that could be used. So there ought to be stations where we might be able to meet this criteria of having, say, 10 recordings and trying to pull out single station sigmas out of those data sets.
Yes, so there's a couple of reservations there because it wasn't a very active aftershock sequence, and some of the stations are vertical only. And there are field data stations where the ground conditions might not be that well known. They were temporary stations. But there is quite a large data set there. At least you were after like 10 events. Well, I think if you went down to about magnitude 2.7, you get 10 events. And those should be recorded out to 200 kilometers region as well.
So I think maybe what we would ask then is you look for those extra stations where you could get 10 recordings that have horizontal so that we're not worried about the vertical only problem, and see if we can then compare those single station sigmas you get out of that. Are you getting this down, Christine?
I'm trying to compare the summary and
Okay, so no is the short answer. All right.
you can write it
That's
down.
fine.
It's been recorded, right?
It's been recorded. We'll go back. So the data that Bob was talking about. So the key is you have a lot of data that we can define attenuation out to 1,000 kilometers. And you indicated some problems maybe beyond 1,000, but it looks pretty well behaved out to 1,000. Nice. Okay. So do you know, again, the same idea, how many sites would you have that might have more than 10 earthquakes? Is this a sparse part of the data set, or is it a large part?
It might be possible in the east, with the transportable array to do that. The real problem is having sufficient data to do a multi-step regression to focus on that. But you saw that one figure I had of earthquakes that I looked at this year. And 10 earthquakes may be possible.
Okay.
Actually, I mean, that would be, at present, what you would get is a nice swath of information in the sort of the Great Plains going down to Texas, that would provide a lot of, that may be useful.
So we could,
So I think data do exist, it is available.
Our main objective in trying to get at some of these single station sigmas again is to see if this remains a fairly stable parameter. So if we can see what it is up in Canada, we can see what it is in the plains.
How many do you need before you've decided it's a stable parameter? Do you need 1,000 stations or would 10 stations be adequate?
We will, how many do we need? I would say it's the order of 10 as opposed to 1,000.
Trivial.
Okay? I wouldn't say 10, but let's, maybe
prefer 100.
I prefer 100, but I don't need 1,000.
You've got it already in southeastern Canada. You have it in the central U.S. already with existing stations. You can sample wherever the transportable array is, and you've got that. So you've actually got two major different geographical regions, two different types of source environments, earthquake sources. Yeah.
Okay, so looks doable, so that's good. Data from other regions that Gabe was talking about. So we had a bunch of,
So you're going to give us this small magnitude data, hopefully several events at the same station and so on. Are these processed data, unprocessed data? Are you going to do the processing? What's the processing issue? Who is going to do it? And
there's a lot sitting in my computer again, but it has to be redone, perhaps. But it may not be a major effort.
Okay. So you're going to get processed according to the same rules that they have, and we get responses spectrals, right?
And you'll get what I'll provide on.
Like it or not.
All right, data from other regions. So it was a little unclear exactly the boundaries of some of these regions, and that's an issue. Do we include, so I mean, this whole issue of large events, which we're after near boundaries, is what is included, and then outside. We have always traditionally brought Nahani along for the eastern U.S., even though it would fall outside your boundaries, I believe, because we're so desperate for big earthquakes codes that look like they're from the east as opposed to being from the east. What criteria should we be using to include or exclude the larger events that appear to be SCR type events? Or have you thought that?
Well, I think for large events, it has to be done on a case-by-case basis, looking at focal mechanisms, the local properties of the crust around that region. Fortunately or unfortunately, the number of those events is not that large, so it can be done. But I think the only feasible way I can see for doing that is on a case-by-case basis.
And is this something that's already in our scope of work right now?
I don't think it is.
It's not clearly defined.
Not clearly, definitely.
So the second year of the data collection, which is October 2009 to September 2011, basically originally was supposed to be focused on international data. However, since we have limited resources, I think we have to optimize it. With the new data that we get from Bob Herman and so on, we have to decide what matters more for us. We cannot do everything in 1 year, Bob, and all international data and so on. So we have to optimize.
But do we is this left up to the database working group to choose, or is there some guidance that Gabe needs to get? How are we going to do this?
We need some direction and some help. Again, I'm an engineer. When it comes to deciding in what tectonic environment these events are in, I'll have to claim my engineering ignorance.
But the real question, before John gets in, is what earthquakes are important? If you talk about earthquakes with magnitudes greater than 6, you must go elsewhere to find them. But from we saw in Gabriel's presentation, there aren't that many. Australia is less than 5. Do we have a sufficient number less than 5 in Eastern North America that we don't need Australia? For questions. Korea is going to be less than 5. Are they necessary? Or perhaps the question is there some aspect of different data sets that are important for scaling? Might be one question that would help select earthquakes, or important for understanding amplitude versus distance at shorter distances. So I think these particular questions have to be answered to make a decision about whether earthquakes outside the U.S. or outside of North America are really of value to this effort.
John. And I guess I'd like to add, I think that's actually the TI's evaluation. It's not really something to delegate to a working group unless you actually push the SSHAC process down into that working group.
So I think the plan for this is going to add a task for the interface with the database working group, the CIP, and the other relevant working groups to define those priorities and then go after what we have decided. So that's the new task on the other hand, right?
Okay, there was also an issue of, let's say, data that have restrictions to them. We did talk about this a little bit again this morning as well. The data sets that we use finally to develop our models have to be available. So I think restricted data is something that we can use to check our models, but we can't say our model was derived on this data and by the way nobody else gets to see it, and the model has to be reproducible. Otherwise we can't use it. So I think we're going to have to live with that restriction of let's say proprietary data or things like that are only used in our own checks to make sure we don't have a problem. If we see there's a problem, then we need to really double our efforts to get the data made publicly available.
One more question. What about, is there any restriction on Australian data? Obviously we can use it, I assume the researchers can use it, but can we post it at a website?
So I guess as I mentioned in my presentation that most of the data that I have is proprietary. I have received support from some of the data owners suggesting that they would like the data to be open. However, there is probably about 1/3 of the data set which I have not passed on to the NGAE effort. And I guess we're still negotiating with the data owners as to whether they support this activity or not.
And I think just our idea of what is proprietary is publicly available. I don't think data sets have to be released by the peer data center. I mean, somebody could say it's their data, if you want it, go ask them for it, and as long as it's publicly available, then we should be able to get at it. Because I know some people in agencies don't want a peer to be distributing their data for them. And that's once it's reprocessed, what is it? That's a very good question that we're going to have to face.
Yeah.
Okay, so what are we going to, our last thing here, what are we going to do and prioritize? As Christine already said, I think we're going to have to sit down and go back to what we can get. But I think now, remember we talked about our priorities this morning of geometrical spreading, right? First 40 kilometers, data that can help us get at that, data that can help define for us median stress drops and any magnitude dependence that's there, we need to really consider as probably our biggest focus for data sets. And then enough data to look at some single station signals in a couple of regions so that we can sample that and see if we can easily transport our models where we have 50,000 data points or something that Bob is going through for California, and just pick that up and move it around, or if that has to be changed. All right, what else do we have? So Australia, I think we were just talking about this. What was the fraction of the data that is provided now versus what you think you have? Because you had said a lot of things weren't yet provided, and
I'd probably say that there's roughly 50% of the data which are provided so far. So 1/3 of the data set probably comes from the Sydney catchment area, which has not been provided yet, and there are also additional earthquakes from Western Australia which also haven't been provided.
And do you have an idea of how many recordings per station? Are there stations with 10 recordings?
Yeah, there'll be several stations, probably in the 10, I would say, of multiple earthquakes.
Oh, she'll talk about that on Thursday, I think.
And
okay.
I guess also I've forgotten about South Australian temporary deployment, so there'll definitely be, most of those stations will have multiple earthquakes as well.
Okay, great, thanks.
So, Bob talked about, Bob Dare at the time, the large set of small magnitude data, and this was all 3 and larger. Is that correct?
Correct.
So that's, I think, another thing for us to think about in looking at other regions. To the extent we can keep it about 3 or larger, then we're able to make a comparison directly between the scaling we're using in California versus the eastern U.S. So that ought to be, if it was a 2.9, I think we can bring it along. If it's an important site or recording, but we don't want to be bringing sort of the 1s and 2s and smaller events along. Okay? And are you really processing by hand 50,000 recordings and plotting up time series?
We use computers, yeah. We used to do it by hand.
It looks,
I have a question about your small earthquake data sets. What are you using for depth? How are you getting depth? I would personally prefer that if you had 3.5 and larger, you're going to have a moment tensor inversion that probably have a better depth than anything from a regional network. And especially if it's going to relate to short distances scaling out in 40 millimeters.
We steal our depths from either Berkeley or Caltech, and we take whatever depths they have in the catalog. And some of those depths, I think for the bigger ones, probably come from moment tensor solutions. Most of them come from the regional networks, which in California we have quite dense regional networks. And from my experience at Berkeley Seismographic Center, we used to think our depths were fairly well constrained, at least in the upper part of the crust.
So Bob is warning on, let's say, accuracy of the depths that are coming out that we need to, the truthfulness of the depth.
As opposed to the number the computer gives.
Okay. I think that's all that I have written down. Are there other issues on database of what's being included or what we need to add? Comments from anyone? Yeah, Mark. You need to come to the front. Sorry. Everybody will be up here in a little bit.
I think for even for the smaller events, maybe particularly for the smaller events, at closer distances, that well-constrained focal mechanisms also need to be correlated with those things.
right now, I think the mechanism isn't in there. Is that correct, Bob?
I think in the table, in Brian's table, sorry. In the table from Cho et al., that information is already there. It was already classified as strike slip, reverse, normal, or oblique. For the additional earthquakes and the aftershock sequences, we haven't got that information yet, but a lot of that should be pretty easily available.
So that should be QA. That has to be.
Thank you.
All right. Any other
Trust but verify.
questions, suggestions? Ralph, you have to come up.
It has to do with the use of, in this small earthquakes, the magnitude 3s in California. It would seem to me like if you really are interested in getting the 1 sigma or something like this, there are plenty of magnitude 3.5s and above. When you go down to magnitude 3, how much, that must add, maybe 10,000 earthquakes. If you really want to do them all. At the present time, the number of earthquakes, following Landers, there were something on the order of about 500 magnitude 3 aftershocks. Following the El Mayor earthquake, there's already something on the order of about 40 magnitude 4 earthquakes that are well recorded. So, and around Southern California with these new, the new distribution of stations, we have a magnitude 4. There must be, I counted at least 5 to 10 magnitude 4.5s, greater than 4 earthquakes already in Southern California, not including the El Mayor aftershock sequence. So it seems to me like anytime you get an aftershock sequence, you get more than enough magnitude 3s, but it's really in that magnitude 4 range that we should be looking for. And I think you can get 1 sigma for that because they're recorded on multiple stations. All these earthquakes are recorded on the same station.
The purpose of the California data is to be able to get a ground motion model for magnitude and distance range that are comparable to the eastern data so that we can compare, let's say, sigma models, for example. So the reason we go down to 3 in California is because we need to go down to 3 in the east to be able to get enough stations. Is that an accurate statement, Bob Herman? How far down do you have to go in magnitude to be able to get 10 stations per 10 earthquakes per station, for example? In the east? Yeah.
3 and lower.
3 and lower. So that's why we're stuck. We're going down to small magnitude.
Is the sigma going to be dependent upon the magnitude, or is it something that this?
We're looking at that in California then. So we're going to take magnitude dependence of the sigma from magnitude 3s all the way up to 7 that we have in California, and then our big assumption is that that trend is going to apply to the east, at least as one approach. And Ken is holding his head, but yes, that's what we're doing, right? So we're trying to make it so that we're comparing the same things in California versus the east. So sigmas from magnitude 3s, California, how do they compare to sigmas from magnitude 3s?
What are these sigmas of? Like the road 50 or what? This is,
Yes, we'll be using that stable parameter, road D50. And I believe that's all agreed upon, right? That's the parameter we're using. But it's better than what we were using. Okay? Progress. Any other questions or comments on what we're doing with the databases? Are there other data sets you're aware of we should be looking at? Or something that we're missing? All happy? Go ahead.
I think Yusef sent out an email to everybody, maybe from Chris, giving a link to his Memphis website that has the flat file. listed? To the chairs. Okay, well, anyway, now that those files are accessible and out there, people can just start to poke around and have a look and see what they think is missing or what's wrong or what's okay.
Yeah, I think that will take some testing it out and seeing if there's any problems that we find or both in the metadata and in the ground motion data. All right?
Some conditions for those stations are coming from geotech working group, is that right?
I think so. I think Chris has given them everything he's got.
Okay, the metadata for magnitude 4 and above for Central East North America, the site condition is coming from geotech working group, not from Chris Crane, right?
He collected whatever he could find and then passed it to the geotech working group, and I think from then on it is the responsibility of the geotech working group to assign those values, yes.
Okay. Other questions? Okay, I think we're in good shape. How is your summary coming?
It's ready.
Okay. All right, class dismissed. Yeah, thank you.
Yeah. We're making good time. Thank you everyone for the interesting discussion on the data issues. I think that's one place where we have a pretty good handle. So, I prepared a short summary of what I think to discuss today, summary of the key issues, and let's go with that. Okay, so I'm starting with the ones that are going to be addressed later, or that were originally in norm stock, that we're going to address later and discuss further later this week. Epistemic uncertainty, we're not going to discuss that this week. It's going to be later in the process once we start assembling the logic tree and all that. The ground motion component, everything is done with GM and D50, but we will compare ratios for the maximum component for the west and the east, and hopefully these will be the same, but that should be an easy thing to take care of. Sigma standard deviation issue is going to be discussed mostly on Thursday, and so we'll keep comments for that on Thursday. Same with vertical ground motion. The path regionalization and correlation of assimilation input parameters, and those are the ones we have not put in the simulations, within and across regions. And this is a kind of a meaty topic. We need to talk about regionalization, the correlation of parameters that are going to be used in input simulations, but also the correlation across different regions. So if you have a geometrical spreading in one region and a cap of another region, then can you intermix them or not? We'll talk about that on Wednesday and see where we're at with that. Side effects regionalization is going to be discussed a little bit on Tuesday when the geotech will talk about their VS profile database, and simulation methods are going to be addressed on Tuesday, mostly in the afternoon. Okay, some of the key issues. So we know that simulations are going to control the hazards because most of the data that's going to be controlling the hazards comes from the simulation. And we have mentioned that it's very important to have clear and well-defined inputs for those simulations, and there's many different topics that relate to that. We talked about stress jobs, and this is going to be discussed further on Wednesday. What is the state of knowledge regarding other stable cognitive regions? We talked about the validation parameters, that they should include more than just SA, although in a forward sense, that's all we're going to predict, SACG, APTV, so that's an important thing, but that's going to be hopefully taken care of by the path simulations group. And so we talked about also making sure that we have a coordinated application of the different numerical simulation methods, so that when these different input parameters and all that. So I just lumped all those issues into that little category there. So So those are things that we still need to work on, and we still need help and to clearly define solutions to these issues. We also talked about the geometrical spreading at short distance, less than 40 kilometers, and it came up in the last discussion that the need to define that should drive at least part of the priority for gathering more data. So we need to constrain it. When we saw the slide from Chuck, there's not a lot of stuff within 40 kilometers. Okay. The site conditions for ground motion stations, that's an issue that's going to be brought up. I don't know to which extent, but with the geotech working group presentation tomorrow, but it needs to be addressed, and that's something that we keep in our list of issues. We will need to define details for the distributions of ground motions and decide whether or not we want to cap those ground motions and whether that cap and how far we go along. Those are things that we need to address as well. We talked about the GMP verification. Whether or not we will constrain them with intensity and liquefaction data because of that circular reference, but we need to decide first, do we need to address it, and if we address it, then how are we going to get all the data necessary to address it right. So there was a task suggested to interact with the SSC group on that. There's also a need that Chuck brought up with QA/QC of the recorded data from the East, and I think that NGA West and NGA West 2 have done quite a bit of work on that. So there needs to be a knowledge transfer right there to make sure that the process for checking is consistent. Then here, the last bullet point is actually should be a few pages long, but I'm lumping everything together here. We always have to keep in mind that with the PATH working group, the geotech working group, simulation working group, we will need to hand up preliminary values either to another group or to GMP working group that's going to be formed through RFP in the next few months. And we need to think about that because we're going to feed prelim values, GMP developers will work on that, and then we'll have final values, hopefully are not going to be different. But we need to make sure that these handoffs are clearly set in time. It's going to be our role as TIC to make sure it's done. But it's really critical to the progress of this project. Regarding data needs, so as you were probably aware, I was kind of trying to summarize things, so I missed a few of the discussions, but we need to see what data we're going to have in the current database. And many issues came up. Well, for example, the geometrical spreading, we want to constrain it, we need more data for that, that's one priority. If we want to compare the sigma or small magnitudes from the west, we should have a similar database, at least that encompasses the same kind of range of data that we have. And there are many different issues related to that, and we'll need to prioritize. And I guess we'll need to decide what data are applicable from other SDR, and if we can use boundary region data and all those things. And I think the best way to address that is with a task to define the priorities. I think it's mostly going to be led by the TI team because it requires integration of many different topics. But this has to be done within the database working group and interaction with the other users of the data, ultimately. So that's what I had for today. In terms of summary of the key issues, I tried to select that into things, and I see this summary as a list that we take away from this meeting of things that once we go back to our normal life outside the workshop, we say, okay, we need to address this. Who's going to take care of this? And these are the key issues that we take away from this. Annie? Yeah, I had that discussion. I guess there was a bit of discrepancy on that. Okay, so Annie's saying basically that after my summary, we're supposed to open the floor to questions. First the TPRP, and then the sponsors, and then the public. And through discussions with various people, I guess this part got thrown out. Sorry, I'm still learning about the SHAC process. At some point, we thought that the PPRP, because we have closed door meetings, that we would address those issues in the closed door meeting. So
Let them ask questions today and we'll figure it out.
okay, so before we go on further with that, do you think, and I'm calling out to everyone here just to tap your brains, is there anything that I left out from the key issues we discussed today? Just quickly to make sure that we got them. Larry? Oh, yeah, okay. Yeah, definitely all of that. So Larry was, I think, the need for the CUS catalog to be SSHAC. Okay. Consistency, yes. Normally taking a note of that?
I already had that added.
Okay, yeah, good. Okay. So I guess this is a time where we welcome comments first from the CPRP, and we're ahead of schedule. So that doesn't mean future speakers that you can prepare for longer slides. Just prepare if we have to time allowed. If we have time to breathe and think, it's all good. So I guess we'll welcome comments from the CPRP first, or questions. Yes, please. So everybody can hear, and the only way that this is recorded is through the microphone. Thank you.
The PPRP has a lot of comments and issues, but we don't need to discuss in an open forum because we're going to have a closed meeting with you. Since they're quite a lot, since we've seen the project plan for the first time, and we have a lot of issues we'd like to discuss, maybe we could use some of the extra time to extend a half hour this evening because we have some fairly fundamental stuff. So I don't propose that we open up those procedural and structural concerns. Open discussion, but any of the PPRP individually may have technical issues they want to raise. Now would be appropriate to do it. I have one while I'm standing here with the microphone, and it's shared by at least a couple of people who I have chance to discuss it with. If you do only single station sigma, it assumes that everyone will apply the models that come out of the project with the right conditions to constrain or represent on a logic tree the repeatable parts of the side effects. And that won't happen, and it will be abused. And it's not clear to me and to some of us why you don't do a sigma and a single station sigma. So that's spoken as that you're doing single station sigma only.
Do you want to address that?
Sure, Linda is going to cover the
yeah.
But yeah, as Youssef had talked about, I think there's more need for the USGS. They want a regular old sigma, so we'll do that one as well. So now we are committed to give you 2 sigma numbers to choose from.
But it's not just USGS. Well, these equations like DNA equations, and only sigma.
All right, so Julian is saying these models will not just be used for nuclear power plants in the United States, but these things get a broader application. And so both single station sigma and vanilla sigma will be provided.
Okay, anybody else on the PPRP on the specific issues from today's presentations and discussions? Yeah, clarification, question, comments that you'd rather address publicly? Okay, so I guess we'll move on to, yes, Trevor Adams.
I guess I've just got something that I'd like to clarify. Who is responsible for assigning magnitudes to the earthquakes that are going into the database? Clearly magnitude has implications for the stress drop, and magnitudes are determined by geometrical spreading and Q factors as well. Is that going to be discussed later in the week?
Central Eastern North America or
all earthquakes.
Central Eastern North America is the region of Cali. Central Eastern
North America earthquake magnitudes, the concept is easy. We get it from Central Eastern Source Characterization Project from Larry. And we already talked in the next few days, we get unofficial version of the magnitude to SHAC and so on. So that's easy. International, I don't know. Very gate, left. Oh, gate.
Gabe, did you hear the question? Okay. Okay, Gabe, go on.
Yeah, actually, I was talking to Bob about that issue for the Canadian event, but apparently we're covered there. But yeah, that's an issue, and that's another complication that you have when you're looking at international data. For example, hearing about the South African data, they're talking about ML for most of their analysis. They're also in the process of calibrating that ML to a moment magnitude. But that's an additional complication. In the Central and Eastern U.S., we're covered with the catalog that Bob Jones has put together, and except against some Canadian events, mainly special treatment, but that's easier because we have the moment tensor solutions from Bob Herman and other things. But yeah, that's an additional problem that we're going to have, we're going to face.
So, yes, you want to add something?
And it should be moment magnitude. For the sake of consistency, we should have moment magnitude for all data we use.
Yeah, that's all we can do. Yeah, so I guess we need to think about this issue, but after we have prioritized which events we will use for additional data, we'll need to find a way to address it. Yeah, we need a vertical. Yeah.
No, here.
What?
So we've done this before on NGA West when we developed our catalog. We had a review by a group of seismologists on the magnitudes, and we'll do the same thing here. So the magnitudes will have to be reviewed. It's not, we can't expect Gabe to go out and set all the magnitudes. He'll tell you he's an engineer, he's not a seismologist, he's just going to read it out of some publication, right? So we need some group that can actually judge the reliability of the magnitudes separately. Sorry, Gabe.
Okay. So if the PPRP is done with comments, we're going to move to the sponsors, and after that we'll open to the floor. Paul, you're done PPRP. I'm sorry. Boss. Okay, any of the sponsors would like to comment on or question and clarification? Larry, why don't you come up? Larry Solomon.
Just a quick comment on one of the earlier slides that was shown very quickly. If my vision is okay, it looked like the study area was a little short and not directly matching the study area for the CUS project. So it's something I could point out that I don't know if it would be significant, but you should look at our study area and then align it because the earthquake was particularly short on the west side of it.
Okay, so regarding this, we'll just need to make sure we have the right interface with the interface advisor from SSB, who's Kevin Coppersmith, and just to make sure that, again, we're consistent. Is that all from the sponsors? Questions, clarifications, comments? Okay, Paul, please. I'm sorry, it's my role. I have to play by the rules. Please come over to the microphone. So we're going to have an extra 15 minutes, possible, maximum, for discussion. And if we adjourn earlier, we'll be happy to discuss with the speaker privately.
I just wanted to emphasize what Bob Herman has said a couple of times, and that is the ideal way to know the size of an earthquake is to use this moment tensor solution based on very, very long period waves.
whose period is so long you don't even have to know what the crustal structure is, right? So you fix the seismic moment, you fix the depth, you fix the mechanism using very, very long period waves, and then you know everything about that earthquake, and that makes a sound basis for then knowing what the source is, and then studying attenuation and source properties and all of those things, right? But if you're using a method that already includes assumptions about attenuation or source properties and analyzing the data from the earthquake, then you get circular. So that's why it is really important. The gold standard of a magnitude is a long, very long period moment tensor magnitude, and Bob determines them very reliably and very stably. Other people who look at the same earthquake frustratingly get the same answer that Bob gets, because it really is a very reliable and robust thing to do. So I would urge, wherever possible, get very long period moment tensor magnitudes, depths, and mechanisms of all of the earthquakes that are being studied, especially in the eastern states.
Thank you. Any other comments or questions? Vladimir, please come over. Vladimir Grazer from NIC.
Thank you. I actually have a very short comment, a question. I saw abbreviation CAD. I guess it stands for cumulative absolute displacement or whatever. Whoever put this, I'm just puzzled what is that. And the second comment, just to suggest, as a suggestion, don't put something which is not known to the community. That's all I wanted to mention.
Ralph, did you want to respond to that? I think you wanted to use the CAD because it's easier to trend and predict, or, but it's just a suggestion.
It's the same as CAD, except you would integrate the absolute value of velocity. With displacement. So
yes.
It would end up giving you the units of displacement. It's the same way that CAD comes about. It's really you're integrating the absolute value of acceleration with dt, so you end up with the units of velocity. So if you integrate integrated velocity seismogram, you know the absolute value of it, you end up with equivalent of CAD.
Yeah, but again, I don't want to go into discussion. We all know what integrated displacement means. It's very unstable.
No, that's not integration.
Okay, so the discussion, I guess, and the point was that we should make sure to use terms that are used and that are recognized. Ralph's point was that the CAD is just the integration of velocity. It gives you units of displacement, similar to what the CAD gives from acceleration. Now, this is so that's the bottom line on that. Any further comments or questions? Kiewa, please come over. Kiewa Sang from USGS.
My question is about the moment and also the magnitude assigned to each of the eastern earthquake or some other stable continental region events. When we assign this moment or magnitude, are we going to have an arrow bar to go with it or the arrow to go with it? This might be a question given in general. So is there any answer to this? Or is that something we're going to address?
That's all part of our peer review of what the magnitude estimate should be. So, other questions, comments? No? If not, we declare ourselves adjourned. All right.
So let me